Okay, this one is a fun one. It has lots of parts to it. So we are given the waveform. The waveform represents the voltage across a 0.2 Henry inductor for t greater than or equal to 0. We have the current flowing through the inductor at negative 20 milliamps at t equals 0. So we have the initial current. So I of 0, and that'll be important, is negative 20 times 10 to the negative 3 amps. And we want to determine the current I of t for t greater than or equal to 0. So we're determining a function. So that means we're not determining numbers, we're determining a function. And if you look at the waveform is in 3 pieces. And so our function is going to be in 3 pieces as well. So we're going to have 3 different pieces for our function, and we have to find them. But first, to do that, we need to find out what our function is. So we're going to see how our function is defined. So we have from 0 to 2. Notice that our function is a straight line with a slope of 10. So when you get to 1, you're at 10. When you get to 2, you're at 20. Or rise over run. So 20 divided by 2. And it's a straight line. It goes through the origin. So v of t equals, well, first of all, it's negative 20 at, oh no, that's not the voltage, that's the current. V of t equals 10t for t between 0 and 2. So just a straight line, 10t. Except this is in millivolts, so that's 10t times 10 to the negative 3. And I'm going to put that in there as a number rather than as an m, because I'll lose track of the m. So I'm just going to go ahead and do it as a number. 10 times 10 to the negative 3. Okay, then from 2 to 3, you might be able to look at that and come up with the equation of the line. But if you aren't sure, just remember from algebra that we have the point 220 and we have the point 310. And so the slope is rise over run. So 10 minus 20 over 3 minus 2, which is negative 10 over 1, which is negative 10. So that's our slope. And then to get the equation of our line, we'll use the point slope form. So we'll say pick one of these 2 points. I'll use the first one. V minus 20 equals negative 10 t minus 2. V minus 20 equals negative 10 t plus 20. V equals negative 10 t plus 40. And this is also in millivolts, so it's negative 10t plus 40 times 10 to the negative 3. So we have negative 10t plus 40 times 10 to the negative 3 for t between 2 and 3. And greater than 3, we have that the voltage is 10 times 10 to the negative 3. Okay, so what do we know about current and inductors? We know that I of t equals I of t naught plus 1 over L times the integral from t naught to t of v of t dt. Now, the purist in me says we should not be using the same variable as a limit of integration and inside our integral. But I'm just going to keep it that way because when I do it differently, it confuses people. But having this t at the top as our limit of integration means that when we finish, when we plug things in, we have a function, not a number. Because people a lot of times want to ask, well, if it's going from 0 to 2, why don't we have 0 to 2 right here? And the reason we don't have 0 to 2 is because we want a function for any time between 0 and 2. We don't really care. If we wanted to know what it was at 2, then we could do that. But we don't want to know what it is at 2. We want to know, we want to have a function for any time between 0 and 2, any t between 0 and 2. And that's why we have the t there. So for our first part, so for t between 0 and 2, I of t, so this means t naught is 0, will equal I of 0 plus 1 over L, and L is 0.2, integral from 0 to t, and that t, like I said, just stays t, and our function was 10 times 10 to the negative 3 t dt. Okay, so we were told in the problem that I of 0 was negative 20 milliamps, so this is negative 20 times 10 to the negative third. 1 over 0.2 is 5. And then 10 times 10 to the negative 3 is 0.01. So this is 0.01. And then when I integrate, I get t squared over 2 from 0 to t. So I get negative 20 times 10 to the negative 3 plus 5 times 0.005 t squared. So that's plugging in the t and the 0, which really just doesn't do anything here because it's 0. And our next step, it won't be 0, which equals negative 0.02 plus 0.025 t squared. Okay, so we have I of t, we're going to get started on this over here, equals negative 0.02 plus 0.025 t squared for t between 0 and 2. Okay, so we've got the first part. I could multiply everything by 1,000 and have it in milliamps. Right now it's in amps. That's in amps. Okay, so now we're going to do from 2 to 3. So in this case, I of t is going to equal I of 2 plus 1 over L times the integral from 2 to t, and then our function here was negative 10 plus 40, negative 10t negative 10t plus 40 times 10 to the negative 3 dt. And I'll take that 10 to the negative 3 out. But first I have to figure out what I of 2 is. So remember, the current can't change instantaneously in an inductor. And so that means whatever, so if we go back and just, this is the voltage, but whatever the current was in this first section, right at 2, that has to be what the current is right at 2 in the second section. So I have a function for the current in the first section, all the way up to 2. Well, I know the current at 2 in this first part has to equal the current at 2 in the second part, because the current cannot change instantaneously in an inductor. Or if you looked at problem 3, I think, the current can't change instantaneously. So if I plug in 2 into my function up here, so I of 2 equals negative 0.02 plus 0.025 times 2 squared, I get 0.08. I think I do. If you don't get that, don't panic. It just means I'm wrong. Okay, so I of 2 is 0.08 plus L was 0.2, and I'll take the 10 to the minus 3 out, and then inside here I get minus 5t squared plus 40t, and this is from 2 to t. So this is 0.08 plus, and then 1 over 0.2 times 10 to the negative 3, I believe, is 0.005. And then if you plug t in, you get minus 5t squared plus 40t minus, and then we have to plug 2 in here. Last time it was 0, so we didn't have to do that. So minus negative 20 plus 80. So this is 0.08 plus 0.005 times minus 5t squared plus 40t minus 60, and then multiply the 0.005 through, 0.08 minus 0.025 t squared plus 0.2t minus 0.3, and then combine the 0.8 and the minus 0.3, you get minus 0.025 t squared plus 0.2t minus 0.22. So with all these numbers, I would be really surprised if they're all correct, but I did try. Okay, so minus 0.025 t squared plus 0.2t minus 0.22 for t between 2 and 3. Okay, so now we have for t greater than 3, and for t greater than 3, the first thing we have to find, just like we had to find I of 2 before, we have to find I of 3 here. So we have to plug 3 into this function that we just found, because this was our function from 2 up until 3, and it can't change instantaneously at 3. So this is minus 0.025 times 3 squared plus 0.2 times 3 minus 0.22. Which looks like 0.155. amps. Okay, so now for t greater than 3, we have I of t equals I of 3 plus 1 over L times the integral from 3 to t of v of t dt, which is I of 3 plus 1 over 0.2. Oh, we know what I of 3 is. 0.155. So the integral from 3 to t of v was 10 times 10 to the negative 3, which is 0.01. Except I'm going to take the 10 to the negative 3 out because I did that last time. So 0.155 plus, and then when I took this out and multiplied to the 1 over 0.2, I got 0.005. And then I just have the integral from 3 to t of dt. Oh no, 10 dt, because I just took the 10 to the negative 3 out. So 0.005. So that's 10t squared over 2 from 3 to t. Oh, it's not t squared because there's no t in there. It's just 10t. Just 10t. Okay, so that's 0.155 plus 0.005 times 10t minus 30. Multiply the 0.005 through, 0.155 plus 0.05t minus 0.15 equals 0.05t minus 0.005. And so that is our voltage on our last segment. So that is 0.05t minus 0.005.